Hey guys, today we're going to look at a special type of t-inference for means, and that's called the matched pairs test. So we're going to review all the way back from semester 1 what we talked about when we discussed matched pairs so that you can understand when to use a matched pairs t-test for means. If you'll recall, there are two different types of matched pairs tests. There are two forms. The first is that we compare individuals by certain characteristics that they share. Maybe two female athletes are paired together that have similar running times, or two male athletes. Remember, in this type of matched pairs test, we randomly select one of the individuals to get treatment A, and then we take the other individual B will be assigned to the other treatment. So in this case of matched pairs, the assignment of treatment B is dependent on who got the assignment of treatment A. So in a matched pairs test, we've actually got a dependence, right? The second person is assigned whatever's left over. The other situation we could have is that our individual people, our experimental units, whatever they are, receive both treatments. In that case, the order that they get the treatments are randomly assigned. So we've randomly assigned them the order of the treatments, or we look at before and after measurements that are taken. In this example of matched pairs, the two measures are actually dependent on the individual. So regardless of which type of matched pairs situation we have, when doing a matched pairs design of a test or inference, we are going to have some sort of dependency in our situation. So I've given you 3 examples on your notes. Let's take a moment to read through the examples and identify whether or not they are independent or dependent, whether or not they're a two-sample or a matched pairs test. So go ahead and pause the video now, read through 1, 2, and 3 on your notes and answer those questions, and then come back to the video when you're ready to go. All right, example 1. A college wants to see if there's a difference in the time it took last year's class to find a job after graduation and the time it took the class from 5 years ago to find work after graduation. Researchers take a random sample from both classes and measure the number of days between graduation and the first day of employment. Is this an example of matched pairs? The correct answer is no. There is no pairing of the individuals. We have two independent samples. We've got an independent random sample from 5 years ago and an independent random sample from last year. There is no dependency, so this is not an example of a matched pairs test. Example 2. In a taste test, a researcher asks people in a random sample to test a certain brand of spring water and rate it. Another random sample of people is asked to taste a different brand of water and rate it. The researcher wants to compare the samples. Is this an example of matched pairs? Again, the correct answer here is no. There's no pairing of individuals. We have two completely independent samples. Now, we could have had the same people test both brands in a random order, and that case would have been an example of a matched pairs design. Example 3. A pharmaceutical company wants to test its new weight loss drug. Before giving the drug to a random sample, company researchers take a weight measurement on each person. After a month of using the drug, each person's weight is measured again. Finally, an example of matched pairs. In this example, we have two measurements on one individual. So in this example, the measurements are dependent upon the individual, and that is an example of a matched pairs test. So today we're going to look at matched pairs inference. When we use paired data, we are actually going to calculate our confidence intervals and our hypothesis tests based on the mean difference for each pair. So we're going to have paired data, we're going to find the difference for all of those pairs, and we're going to average those differences and get a mean difference for our sample. So what we're really looking at here is a sample of differences, and we calculate the mean difference of that sample. So when it's all said and done, we're actually going to be only looking at the differences, so this is going to be set up exactly the same way as a one-sample t-test and a one-sample t-interval for means. The assumptions and calculations are the same as one-sample t-inference. So we're going to go through a complete example. We're going to do assumptions, hypotheses, calculations, and conclusions, and that'll be the end of this video. There will be another video with an additional example if you have additional questions. So let's get started. A whale watching company noticed that many customers wanted to know whether it was better to book an excursion in the morning or the afternoon. To test this question, the company collected the following data on 15 randomly selected days over the past month. Please note these days are not consecutive. We've numbered them. The day 1 represents the first day we looked at data, day 2 the second day. This does not represent the first, second, third of the month. So on each of these 15 days, you'll notice a measurement for morning, the number of whales spotted in the morning, and you'll notice the number of whales spotted in the afternoon. For example, on day 8 whales were spotted in the morning and 10 whales were spotted in the afternoon. So each of these are examples where we're looking at matched pairs data. Since we have 2 values for each day, the values are dependent upon which day we're looking at, making this matched pairs data. So we're going to be paying attention to the differences in the whales morning and afternoon for each of the 15 days. We can actually find the difference for each of these days and use that information to do our inference. Now it's possible that we can subtract either way. We can do morning minus afternoon or afternoon minus morning. The only difference here is depending upon the way I subtract, that will impact my alternative hypothesis. So we're going to do this one together so that you can understand how we subtract and how we calculate the alternative hypothesis. In this example, I'm going to do morning minus afternoon. So let's go ahead and take a data for each of those days, do the morning whale watching minus the afternoon, and get a difference for each of the 15 days. Pause the video to take a chance to do that, and then come back when you're ready to go. So here is our data for each of the 15 days, morning, afternoon, and the difference. Remember, we took each morning calculation and subtracted the afternoon. So on day 2, 9 whales were spotted in the morning, 10 in the afternoon. 9 minus 10 gives us a difference of -1. Remember, we could subtract the other way, but if you did that, your hypotheses are going to be different. So for this example, please do morning minus afternoon. All right, in order to do a hypothesis test, we first need to state our assumptions. We said before that these assumptions are going to be the same as a one-sample t-test, but the assumptions are based on our differences. That's the one sample of data we're looking at. So make sure when we write our assumptions, we're going to use the difference data in order to calculate our hypothesis test. So our first assumption is that we have a simple random sample of days for whale watching. Sigma is unknown. This is a sample, not a population. And we can also say, since the normal probability plot is approximately linear, the distribution of differences is approximately normal. Remember, my assumptions are based on differences. So when I'm talking about a normal probability plot, I'm actually looking at a normal probability plot of differences. Here is an example of the normal probability plot for each of the differences. My biggest difference is -2 up to 2, so -2, -1, 0, 1, and 2. That is shown here in my normal probability plot. Now you'll notice on the normal probability plot we have a vertical stacking of numbers. So at -2 you have multiple blue dots that represent multiple samples that all had a difference of -2. This is called granularity. If I have granularity, this does not affect the linearity of the relationship. Okay, so with granularity, the same value at the same difference is fine. We still have a nice linear relationship in our data. Granularity does not affect that. All right, so we're looking at just these differences, and we need to ask ourselves, is there sufficient evidence that more whales are sighted in the afternoon? So our question is whether or not more whales are sighted in the afternoon. Remember, we did morning minus afternoon. So if more whales are sighted in the afternoon, we would get a difference that is negative. Be careful when you write your alternative hypothesis. If the afternoon is more, the differences should be negative here. But if you had written that the opposite way, your alternative hypothesis would be different. So we subtracted morning minus afternoon. So we're looking at our null hypothesis, nothing going on here. That would be the mean difference, or the average difference in whales, morning minus afternoon, would be 0. There is no difference, status quo, nothing to look at, nothing going on. We're really testing whether more whales are sighted in the afternoon. If that's the case, we expect the difference to be less than 0, or a negative difference. Remember, we have to define our variable here. So mu d is the true mean difference in whale sightings, and we have to specify which way we've subtracted, morning minus afternoon in this case. Be sure to always define your variables when you're writing a hypothesis. Our mean difference is 0, since the null should be that there is no difference between the two. Had you subtracted the other way, your alternative hypothesis would have changed. Your null hypothesis would be the same. All right, let's go ahead and do our calculations now and finish this hypothesis test. We said that our calculations are the same as a one-sample t-inference or a one-sample t-test for means. So we need to calculate our t-test statistic. Remember, that's our statistic minus the parameter divided by the standard deviation of our statistic. Or by formula, we're looking at x bar minus mu divided by s over the square root of n. It's really important that we're showing the calculation for the AP Stats test so that we can get credit for naming the test that we're performing. If you look at your calculations, we see our sample difference is negative 0.4. Our mu, or our difference for our null hypothesis, was 0. The standard deviation is the standard deviation for the sample data divided by the square root of 15. We have 15 days. Since this is a one-sample t-test, our degrees of freedom is our sample size minus 1. We got a t-test statistic of negative 0.945, and the p-value associated with that is 0.1803. All of these calculations are exactly the same as a one-sample t-test. Our alpha, or level of significance in this example, is going to be 0.05. So in looking at this, we want to calculate our conclusion. Now remember real quick here, you got a negative 0.945. Had we subtracted the other way, remember we're doing a lower tail test here, so our t-test statistic is negative. Had we subtracted the other way, afternoon minus morning, we would have been doing an upper tail test, and we would have gotten a t-test statistic of a positive 0.945. Because we would be doing an upper tail test, we would actually get the same p-value here. All right, let's write our conclusion. Since our p-value is greater than alpha, our level of significance, we will fail to reject the null. That means there is not enough, there is insufficient evidence to suggest that more whales are sighted in the afternoon than in the morning. Now, we really want our test to be powerful when conducting a hypothesis test. Remember, power is our ability to correctly reject the null. How could we improve the power of this test? Well, remember, one of the best ways to increase the power of the test without affecting my type 1 and type 2 errors is simply to increase the sample size. That concludes what we're looking at today for a matched pairs test, very similar to a one-sample t-test for means. But remember, in a matched pairs test, we're looking at the average difference. So we're finding a difference in our pair data. We're taking the mu of that difference, or the mean, or the average of that difference. I'm going to do a separate video on another example. I'll also link to some websites and other information online if you have additional questions. Thanks, and bring any questions you have to class so I can answer them. Bye, guys.